Vertical shifts occur when a number is added to a function or subtracted from a function. Vertical stretching and shrinking occurs when a number is multiplied by a function. So for example, our base function here is y equals x squared. If we're looking at 2 times x squared or 1/2 times x squared, then we expect the graph to show vertical stretching or shrinking. So let's take a look at our base function. It passes through the origin. It also passes through the point 1, 1 and the point 2, 4. When we multiply the function by 2, all of those y values get multiplied by 2. So multiplying 0 by 2 doesn't change anything, and therefore that x-intercept, which happens to be the origin in this case, doesn't change. But we can see that the point 1, 1 did move. It moved up here to what we would identify as 1, 2. And the point 2, 4 moved way up here to what we would identify as 2, 8. It's kind of off our grid, but we can see that it's going in that direction approximately, right? So what happens when we multiply a function by a number is that for a fixed x value, all of the y values get multiplied by that number, and that has this stretching effect on the graph. Now, because we're looking at a parabola in this case, and a parabola doesn't have endpoints, it keeps going, but we're only looking at it in a fixed window, you can think of it like stretching a rubber band. If you stretch a rubber band, it does get taller, but if you're only looking at a fixed window, what you notice is that it appears more narrow. So the graph actually became taller, but it appears more narrow. That narrowing effect doesn't happen with every vertical stretch, but it does tend to happen with the graphs that go off to infinity. If they don't have any endpoints, very often what you will see of it, because you can't see a graph get taller if its ends already go to infinity, with the effect that you see more is the narrowing. Now if we look at this last graph, we're multiplying each y value now by 1/2. We can see that again 0, 0 doesn't change. So that x-intercept stays the same in a vertical stretch or shrink. And this point here is 2, 2. This is actually what came from the point 2, 4. So the point 2, 4 became 2, 2, and the point 1, 1 is harder to locate here because it's now at a fractional value. The point 1, 1 is down here at 1, 1/2. So again, for fixed values of x, the y values are all cut in half. This is what we might call a vertical shrink. And again, because the graph keeps going, we don't really see it get shorter in the vertical shrink. We see it get wider, much like an elephant came and kind of stepped on the parabola, pushing it downwards makes it widen. So to summarize our vertical stretching and shrinking, in both cases it is a number multiplied by the function. If that number is greater than 1, we're going to see what we call a stretching effect. And if that number is less than 1, then we see what we call a shrinking effect. But the idea of the graph appearing more narrow in a stretch or appearing wider in a shrink doesn't apply to every shape. So let's see what happens in this case where our graph has endpoints. All right, just darkened those axes a bit to make sure they show up. In this first example, we want to multiply all the y values by 2. This is going to be a vertical stretch. In the parabola example, the only x-intercept was at the origin, This time we have two x-intercepts, so it's easier for us to emphasize on this graph. In a vertical stretch or shrink, those x-intercepts do not move. They are locked in. So we lock in x-intercepts for a vertical stretch or shrink. That's one of the big things that distinguishes it from a shift. Probably the most common mistake with a vertical stretch is treating it like a vertical shift. So I want to make sure that my stretch graph still passes through these same 2 points. I'll start with this point up here. This is at -1, 2. It is 2 units away from the x-axis. I'm going to stretch it up to 4 units away from the x-axis because I am multiplying my y values by 2. Then I will go on to this point down here. This is 2 units away again, but below I'm going to stretch it also to be 4 units away, still below. And now I'm going to connect these points with line segments because my original graph had the points connected with line segments. So this graph really does look taller. It doesn't really look more narrow. That's because this graph didn't go off to infinity. We really see the vertical stretch making the graph taller in this case. Looking at the next one, we have another vertical stretch, or we can use the vertical stretch that we just did. And we're combining that with another transformation. Subtracting 1. Anytime we're adding or subtracting a number, we know that that's a shift. So when we're looking at a shift, we have to first figure out horizontal or vertical, and after we figure that out, which direction within that limitation. So this one is subtracted directly from the x variable. That means that the movement is in the x direction, which means that it is a horizontal shift. We remember that the horizontal shifts always go in the somewhat counterintuitive direction. Subtracting a number would make me think positive, or rather it would make me think negative direction, so I know this goes positive direction, therefore this goes right 1. I'm going to take the stretched graph that I already drew and shift it right 1. So this first point here, which was at -3, 0, it's going to come to -2, 0. I can kind of draw a little shadow, right? Sometimes these shifts are a little bit easier to do on the same grid first, and then see where we are and redraw the whole thing on our new grid. So this looks like it starts here, comes up to 0, 4 on the y-axis, and then drops down to this point down here in the corner. And this is my graph after both stretching and shifting.